This is joint work with David Binder, Ingo Skupin, Tim Sübergroup, and Paul Downen, all of which, except Paul, are also here at the conference. So this is a talk about the structure, about program composition, and more specifically about the structure of typing rules. And to explain the title and make sure that we are all on the same page, let me remind you of what left, right, introduction, and elimination refers to. It refers to the structure of proof rules or typing deduction rules or typing rules, and it refers to whether the main logical connective that we are talking about is below the bar or on top of the bar. That's the difference between introduction and elimination rule, or whether the connective shows up on the left or on the right of the turnstile, which gives us left and right elimination, left and right rules. Okay, so the setting that in programming we are most to is that we have right introduction and right elimination rules. That's the basis of natural deduction, the lambda calculus, and so forth. So that's by far the most studied kind of rule system. The sequent calculus is another very common variant where we have only introduction rules, but left and right. In this talk, we are interested in all these four calculi, including the possibility to have only left introduction and left elimination rules, or only left introduction and left elimination rules, or only have elimination rules. Okay, so the refutation calculus and the elimination calculus. Why are these interesting? Well, we think they are interesting because each of these calculi implies is a different setting. It implies a different kind of program structure. So, for instance, what we have in natural deduction is that we have that we are always computing with an implicit output. When we have nesting of expressions, well, the result of computing the inner expressions flows to the outer expression. It's an implicit output or implicit continuation, we could say. Symmetrically, in the refutation calculus, we are dealing with an implicit input. So that's very symmetric. If we have the sequent calculus, then we have programs that consist of constructors only. Famously, we have the sub-formula property, and computation kind of happens from the outside to the inside. If we have a statement or command, then that's the way the computation goes. Maybe the strangest calculus is the elimination calculus, where we have only destructors, where we have a kind of super formula property, and the computation is more inside out. Okay, let's make this a bit more concrete and let's look at some examples. So, for instance, here is a little program that swaps the component of a binary sum z using natural deduction right rules. So this is something we are all very familiar with. Those of you who are familiar with computational sequent calculi will also recognize how we can do this in using only introduction rules in something like the lambda bar mu tilde calculus. There we have these double bars. They denote commands, and on the left hand of the double bar we have a producer term, and on the right hand side we have what we call a consumer term. And here we see this match. That's the left introduction rule of the sum, and we match it, we put it against the input z, and then in the bodies of the pattern matches, there we have again commands that send the result right x to the output alpha. So in this setting we have named output. We no longer have an implicit output, but we need to give every output a name. Okay, let me show you another brief example to illustrate the influence of this rule choice on program structure. So here we have we are considering a computation where we have a product type and we have an X inside and we need to navigate to the X, and we want to produce a sum type as an output, and we need to inject the X into that sum type alpha, or into the output alpha. And here we see the maybe most familiar form of how we do that in natural deduction using only right rules. So out are the right elimination forms of the product, and in is the injection into the sum. And here in gray, I put the output there because in natural deduction we have this implicit output, but I put it there just to make it clear. Okay, if we do the same using only introduction rules, then we can no longer use right rules, elimination rules, of course. So instead we have to use left introduction rules of the product. These are the consumers of the X, and then inside, you can't see the cursor, inside we need to reify the currently consumed value using this mu tilde operator, which gives the name to the currently consumed value, and then we can use the right introduction rules of the sum to construct the result and send it to alpha. One interesting thing here is what I want you to watch out for is the sequence of the indices. So here we have 2, 1, and here we have 1, 2. So the structure is kind of the order in which we traverse is kind of reversed from inside out to outside in. Okay, using only left rules, this becomes a little bit simpler. Note that I'm overloading the names in and out here for reasons that we will talk about later. So in always refers to introduction rules and out refers to elimination rules, and we use them for both products and sums. Okay, but what I want you to notice here is that here we have again a different order, 1, 1, 2, as opposed to 2, 1, 1 in the line above. And finally, if we only consider elimination rules, we have kind of the fourth possible way to sort these indices. So if we look at the resulting program structure, we see that these 4 calculi correspond to 4 very different ways to structure the program, to compute from the outside in or from the inside out. I think that this also ties in nicely with recent discussions about how to design programs, how to design co-programs. There's these discussions about how to teach programming, whether they should follow the structure of the input or the structure of the output and so forth. And I think these kinds of things are very clear here. Okay, so let's get a bit more formal. So we have developed a calculus in which all these rules can be expressed, and you can put them all together, or you can only use a subset of them. And there's a couple of core rules that are on this slide, which are just the standard rules from the lambda bar mu tilde calculus. So we have these 3 forms of rules. One to, sorry, the cursor doesn't work. One form of rules for producer terms, one form of rules for consumer terms, and then on the right we have the cut rule, which cuts the producer and the consumer of the same thing together. So I guess many of you have seen these kinds of rules before. So let's look at an example in this case of the sum type, what the typing rules look like. So we have the familiar right introduction rule for plus. The right elimination rule is also pretty much standard, except that the bodies of the cases, that they are commands instead of producer terms. So we have CI instead of EI. And the reason for that will become clear soon. But I mean, it's trivial to encode the traditional case with this. So command is strictly more powerful than just the producer term. The left introduction rule is basically like the right elimination rule, except that we don't have a term to discriminate. That happens on the other side of the cut. And then we have a left elimination rule, which takes this form. We have a consumer f of type T1 plus T2, and then we can project out of that sum. Okay, so one of the interesting results in our work is the notion of what we call bi-expressibility. What we mean by that, that's a kind of criterion to make sure that all these rules are in sync with each other. And specifically, that means that we can encode each rule with the rule diagonally opposed to the rule using only the diagonally opposed rule and core rules. So for instance, the right introduction rule can be encoded with mu and the out I left elimination rule. And one thing that is important here is that in all these encodings, no information is ever duplicated or eliminated. And the same works for all the other rules. We can always encode each rule by its diagonally opposed rule. And here we see also why the bodies of the case and match, why they need to be commands and not producer terms or consumer terms, because otherwise this diagonal encoding wouldn't work. Okay. Another main point of our paper is the usage of what we call the proof refutation duality. The basis of this duality is from a paper from Luca Tranchini from 2012, which is a kind of natural deduction style calculus. Logic calculus is not about programming, it's only in the logic domain for refutations. And what's compelling about this work is that he set up a refutation calculus that looks exactly like the natural deduction calculus that we know of, except that all connectives are replaced by their respective duals. For instance, this is the derivation rule for refuting disjunctions. Yeah? So the introduction and elimination rule. And we see that it looks exactly like the standard conjunction rule in natural deduction. So this gave us the idea that we could have a kind of polymorphism where we compute, where we interpret every proof of a proposition also as a refutation of the dual proposition. And that means that we get the ability to interpret terms polymorphically with respect to proof refutation, or equivalently producer consumer. So let me show you an example. So from the typing rules for plus that we just saw, we can mechanically derive the typing rules for this product type. And here we also see now why we have chosen the same constructor rules, because then we can interpret the same program in two ways. And we see that it works with very nicely with all the typing rules. They are exactly dual, and we can use exactly the same term syntax for it. Okay. I think I will skip over the positive conjunction and negative disjunction because I want to use the remaining time to talk about something else. Namely, we have developed a practical or somewhat practical programming language that we call Duo that is very much inspired by this work. And we see a screenshot here of where we translated the program from above to this language. It doesn't have, it generalizes products and sums and so forth to arbitrary data types and arbitrary co-data types and general pattern matching and general co-pattern matching. And we can use all these combinations of rules together. With regard to producer-consumer polymorphism, we have a first step towards that as well. I wanted to show you a brief example here. So for instance, this is a function that's basically the call CC function written in Duo. And what we can do in Duo is that we get a quick fix and then we can say dualize this term and it will automatically generate kind of co-call CC or co-Pierce law, which is basically the same, the exact dual of the program. I mean, that's not really, that's a very ad hoc way of reusing the same program, but yeah, but that's at least the first step towards that idea. Okay, so let me conclude. We have identified these 4 equally expressive subcalculi corresponding to different programming styles. We have shown that they can coexist and interact, and we have proposed this new idea of consumer-producer polymorphism. You can try out our language Duo, which is very much unfinished, but if you still want to try, this is the URL. A better idea would be to ask us at the conference for personal demos. Okay, I think that's all. Thank you.